This PowerPoint presentation is from section 14.6 of our textbook. This fourth video in the series for this section will walk through the calculations of how to prepare a buffer of a given pH value and total buffer capacity from a weak acid and its conjugate base. The following problem is from the Chapter 14 lecture notes. How would you prepare 1 liter of a pH 4 buffer with a total concentration of 1 molar from formic acid and sodium formate? Formic acid is a liquid with a density of 1.220 grams per milliliter, and sodium formate is a crystalline salt. The pKa of formic acid is 3.74. First, remember that if you want to make a solution of known and precise concentrations, you need to use a volumetric flask. In this case, we need a 1 liter volumetric flask. The two components of our buffer are formic acid and sodium formate. The formic acid is provided as a pure liquid that has a density of 1.22 grams per milliliter. The molecular weight of formic acid is 46.03 grams per mole. Liquids are typically measured using volumetric or graduated pipettes. The sodium formate is a crystalline solid and has a molecular weight of 68.01 grams per mole. We will weigh out an appropriate mass of this solid to make our solution. Let's review the question and write down the given information. The acid component of our buffer is going to be formic acid. It has a pKa of 3.74. The base component of the buffer is the formate ion, which we'll get from sodium formate. The target pH of our buffer is 4.00. We also know that we want the total concentration of acid and base components to be equal to 1 molar. And finally, the total volume of our buffer solution will be 1 liter. We're going to use the Henderson-Hasselbalch equation to determine the ratio of the acid and base components that will be needed to achieve the desired pH. We'll then combine this with the buffer capacity information to determine the precise concentrations of each component needed. Let's start with the Henderson-Hasselbalch equation. We know that our target pH is going to be 4 and that the pKa is 3.74. The base component of our buffer is the formate ion, and the acid component is formic acid. We're going to solve this equation for the ratio of the acid and base forms. First, we'll subtract 3.74 from both sides. And then we'll take the inverse log of both sides. Notice that the Henderson-Hasselbalch equation only allows us to determine the ratio of the two components. To find the actual concentrations that we want, we'll have to combine that with our buffer capacity information. I'm going to rearrange this equation here by multiplying both sides by the formic acid concentration. This gives me an equation in terms of the formate ion. And I'm going to plug that in with my buffer capacity equation. So I have the formic acid concentration, the HA, plus the A minus, but for A minus, I'm going to plug in this expression. And those are going to add up to 1 molar. Combining the two terms on the left side, and then dividing both sides by 2.8197, tells me that my formic acid concentration is going to be 0.355 molar. To find the formate concentration, I can go back to my original equation. The sum has to be 1 molar. So the concentration of formate that I want is 0.645 molar. So combining the Henderson-Hasselbalch equation and the buffer capacity equation has allowed me to determine the concentrations of the two components. I still need to figure out how much of each compound I'm going to be putting into my volumetric flask. I'm going to go to the next slide here to give us some more space. So remember, we're looking for a formic acid concentration of 0.355 molar. And a formate concentration of 0.645 molar. We also know that the total solution volume is going to be 1 liter. If we remember from the definition of molarity, molarity is the moles over the volume. So if we solve that for moles, we'll get concentration times volume. So we'll use this equation to go from concentration of each species to moles of each species. We'll then use the molar mass to figure out how many grams of each species we'll need. Because the sodium formate is a solid, we can stop there. But for the liquid component, we'll use the density to convert this to a volume. So here we have our unit plan for finding the amounts of each species that we need to add. Let's start with the formic acid. We want 0.355 moles of formic acid per liter. We're going to be making 1 liter of buffer. And we know that formic acid has a molar mass of 46.03 grams per mole. Canceling units, we figured out how many grams of formic acid that we want to add. But since this is provided as a liquid, we're going to continue and include the density so that we can convert this to a volume that we can dispense with our pipette. Multiplying that all out, we find that we'll need to add 13.39 milliliters of the formic acid liquid. In terms of the sodium formate, we want to add 6.45 moles of sodium formate per liter of solution. We're going to make a total of 1 liter of solution. The molar mass of sodium formate is 68.01 grams. Notice that we're using the molar mass of the whole sodium formate, including the sodium. We can't go to the shelf and just grab the formate. Formate comes as a solid salt that has the sodium counterion. So we need to include that mass in our molar mass. Next, we'll put in the molar mass of sodium formate. Whoops, we have that already, sorry. So we're actually finished, and we get that we're going to need 43.87 grams of the sodium formate. To finish this problem off, we'll describe what we'll be doing. To make our solution, we're going to add 13.39 milliliters of the formic acid liquid, using a conditioned graduated pipette. To our 1 liter volumetric flask. We will also add 43.87 grams of sodium formate to that same flask. Next, we'll add a small amount of deionized water to dissolve the solid and mix the two components. We'll continue to add DI water with swirling. Until our meniscus reaches the calibration line. I've run out of room, but the last thing, of course, is to cap the volumetric flask, invert it several times to mix it thoroughly. In the next video, we'll walk through the calculations for an example of how to make a buffer from just one of the buffer components and using a strong acid or base to generate the conjugate species in situ.